Welcome to week 10 of Contemporary Political Analysis. In this week, I want to focus on multiple regression basics. I'm going to start by talking about what multiple regression is, how it's different but related to bivariate regression, which we covered last week, how we can actually interpret the results that our statistical software gives us, and how we can turn those results into a table that we can use in a paper, report, or journal article. So let's go ahead and start. I have three motivating questions for this week. First, why should researchers move from bivariate to multivariate regression approaches? How do we do so? How does the regression equation differ from bivariate to multivariate regression? And how do we interpret those results? So let's go ahead and really tie it back to what we talked about in previous weeks. The first couple of weeks of the class in the Kelstead and Witten textbook, they presented four causal hurdles that as an argument and research design needed to pass in order to really approach explaining an outcome using causal inference. The first is you need some basic credible causal mechanism linking your explanatory factor to your main outcome. If it doesn't make sense, if your argument depends on aliens landing on Earth and manipulating society, that's not really a credible causal mechanism. We need to be able to make an argument about why our explanatory factor has an effect on the outcome and what actors or structures are behind those connections. What story can we tell that we can link to the previous research that shows that it's plausible and it could be an important causal mechanism. Our second causal hurdle is ruling out endogeneity, that we need to make an argument that suggests that our outcome is shaped by the predicting factor and not the other way around. So if we argue that the electoral institutions increase or decrease the risk of election violence, endogeneity would be that election violence also has an effect on electoral institutions, which could be the case over a longer period of time. But if you think about and try to control in your empirical approach, that you can make sure that the causal arrow goes in one direction, either by lagging our independent variables because times arrow only goes in one direction, or thinking about how the variables are measured, we can try to minimize the risk of endogeneity. The third causal hurdle is covariation. If there is no change in either the outcome or the explanatory factor, a constant cannot explain a variable. You need to have variation in both your outcome and your independent variable. You need to see how these two variables are shaped, how the independent variable shapes the outcome variable. Our fourth causal hurdle, the one that's the focus for today, is have we controlled for potentially important confounding variables that could lead a relationship to be seen as important, but that is really spurious. So if you have your x variable, you argue, explain your y variable, if that seems to be the relation empirically, but then you have a third variable, z, that actually has an effect on both x and y, then you might attribute incorrectly the relationship going from x to y when it's really that background z condition that's having that's driving the observed relationship. Okay, so now that we have those fourth causal hurdles and we can finally now, 10 weeks into the course, be able to control for other potentially important factors, this will enable us to hold other things constant to really isolate the independent effect of our main x variable. And so, as I've mentioned in previous weeks, experimental methods are the gold standard in which you can rule out other factors affecting your outcome except for your treatment variable. But in observational studies, ones that we focus on in most of political science, uh, by through this multivariate framework, we're really able to pass that or potentially pass that fourth causal hurdle for the first time. All right. So, what does it mean to control for other factors? Experimental research designs, as I mentioned, control for those factors through random assignment of your sample into treatment and control groups. So, by that random assignment, you can have confidence that other potentially important explanatory variables are not relevant to shaping the outcome because it is that random assignment of people or other outcome or other types of observations into treatment and control groups. This, as I said, is the gold standard. What we have to deal with more often than not are observational research designs. We take data out as we find them in the world. We can't shape them. We gather them ex post or during. The way that we can control for confounding factors is by adding them to the regression models that we run to try to look at the effects of our main independent variables on our outcome. So this involves thinking theoretically, as we've done in this class, thinking about all theoretically important or relevant factors, and then try to find an observable or measurable indicator of them. Some things might be easier to mention, like voting regulations. Others might be harder to measure, like culture or democracy, in which you might have different people conceiving of the outcome in different ways. So you want to try to find the best observable or measurable indicator of the factors that you want to actually measure. Last week, we talked about the bivariate regression model, in which you have your outcome y, that is explained by the intercept component, where the line that we're drawing, the fitted line between your x and your y variable, intersects the y when x equals to 0. Y is the main outcome, x is the main explanatory factor. The beta is the estimated relationship between x and y. It is the slope of that fitted line. And the U is the population error term or residual that we assume is not systematically biased, and that they with the residuals will cancel each other out in the long run. Multivariate regression models are where it's the same thing. You have the same outcome, the same main explanatory variable, but then you add another variable, z. It's an additional explanatory variable that could be theoretically important, or a control variable that's not directly theoretically important to your argument, but that has been found to be important in previous research, or that you think could also shape the outcome, and thus need to experimentally control for it. The intercept, or the alpha, is a bit different in the multivariate model. That's when you hold both x equals to 0 and z equals to 0. That would be the expected value of y. These models hold for more than one z. Today, I'm just focusing on adding one additional variable to make it two independent variables, but the same processes we're going to follow will also hold by adding additional control variables. And most research that you'll see coming out in journal articles or in books are often having many more than just two variables, two x variables in their models. The betas, what they're actually measuring is slightly different. I think it's important to spend a bit of time on. Beta 1 is the estimated effect of x on y, holding constant the effects of z, and B2 is the estimated effects of z on y, holding constant the effects of x. And so this connects to the ceteris paribus assumption that we talked about in the bivariate regression models, that holding all else constant, this is the estimated effect of your x on your y. And the U, again, is the population error term or residual. And so the important thing to note here is that each of those betas is the independent effect of that variable holding constant the effect of the other variable, in this case, z. Yeah, so I already focused on that. A couple of things that are worth noting. First of all, in the equations, we've added subscripts to variables that weren't needed in the bivariate approach. You see the x, I, and zi, but then also you have beta 1 and beta 2. When you only had one variable, you didn't need that subscript. What the I does is that it tells us that the equation is for each observation of our variables xi to xn, and then the variables themselves, we're just showing the letters here, but they actually represent a vector or a column of observations. In workshops, we dealt with data sets we started with only 7 observations, but now we're building up to hundreds of observations, and you represent all those different values with that one letter. Second thing that's worth noting is the estimated slope. The estimated slopes for your main independent variables x can change by the inclusion of that additional variable or variables, and it can change in 4 different ways. The initial estimated relationship is statistically significant in a bivariate model, but it's no longer statistically significant when you control for other factors. I think this is probably one of the most common outcomes I see when I add additional variables in my models. Or it could go the other way, that the initial estimated effect of x on y was not significant initially, but becomes statistically significant when you control for an additional factor. And with the other 2 potential effects, that it could be increasing or decreasing substantive significance once you control for the other factor. That estimated relationship, that slope, that fitted line, could either get steeper or shallower once you control for the other factors. How do we actually estimate these equations? What hopefully you've seen over the last several weeks is that you start with a basic kind of measures of dispersion, variance, standard error, that distribution of observed values and their relationship to the central tendency. Initially, it was the mean value, and it continues on here as well. In this 2-variable regression slope, you see that it's basically the sum of the differences between the observed value and the mean value of either your x or your y over that squared version, that squared term of the x minus x bar. But with the multivariate regression slope, it is now x hat and y star hat over that xi minus x hat I. And this is with the x hat, that is the predicted value of x based on z, or z. And so that's that leftover. That's the expected value of x given the already established relationship with the other variable. And so what this allows us to do is look at the difference between the expected value of your x variable given that additional third factor. So you can isolate that additional impact that x has on its own. And then the y star hat is that already estimated relationship between the z and the y. So you get that predicted value. The other thing to focus on is avoiding multicolinearity. This is a big word, but it means it's a simple concept that it's a perfect multicolinearity is when you have a correlation coefficient of 1 between 2 of your independent variables. And so if that happens, one of your variables will be dropped out, or because the regression can't work, because basically those estimated relationships, when you look at the additional effect of x given y, it'll be the same thing, right? And so that end up drop out and equals to 0. So perfect multicollinearity is when there's a linear relationship between two independent variables. Some examples of perfect multicollinearity include spatial variables. If you have predictors for both EU and non-EU countries as separate variables instead of one variable, or temporal, like you have Cold War, post-Cold War variables in there separately, then they'll be perfectly negatively correlated. When one is in one group, it won't be in the other. And so that'll end up just having to be dropped by the statistical software. Uh, and so one will automatically be dropped. However, often you get variables that might not be perfectly correlated, but that are quite highly correlated, and then that will end up distorting your parameter estimates. It can distort it either downwards or upwards in the coefficient size or in the statistical significance. There's various tests for multicollinearity. After you run it, there's problems and there's debates about those, but initially, as a first cut, I would create a correlation table of all of your independent variables and look at those Pearson's correlation coefficients, especially ones that are relatively high. I would say there's different people will have different thresholds for that, but above zero point 0.8, I would look at them quite closely.